get right into it. First thing that we'll get into would be the slides. Let's understand how the classical computing model can be converted into the quantum. So let me just share my screen. I hope you can see my screen. Yep.
Yeah.
Perfect. So I won't be spending too much time over here because I've heard that you guys have already done about 3 weeks worth of Qiskit material and quantum computing material. So this is more like something for your reference. So as you probably know, a qubit can be represented as a point on a block sphere. So every point on top of a block sphere would be a pure state, and it would be represented in that form, where 0 is the 0 state and 1 is the 1 state. And mathematically, we use linear algebra to understand what is happening. And how do we do that? A 0 state would be column vector 1, 0, 1 state would be column vector 0, 1. And similarly, you can go look at multiple qubit states as well. And Kronecker product is used whenever you want to combine different operations that are happening on different qubits and represent it as a single operation happening on all the qubits at once. And this is slide number 5 is basically something that you can come back to whenever you need to look at the matrix of how this specific operator looks like. And slide number 6 would be an understanding of the difference between doing operations on the same qubit and on different qubits and how that matrix changes whenever there's a difference. And okay, cool. So right now, to understand Grover's algorithm, you will only require about 3 or at the max 4 gates. And the first gate would be an X gate, which is classically understood as a NOT gate. So if it's a 0, the state, then it'll change it to a 1 state. If it's a 1 state, it'll change it to a 0 state. And you can see how that's happening when you multiply this matrix with that column vector representation of that specific state. And the H gate is a very interesting gate because it is the gate which puts the state in superposition. That's what as Rahul has mentioned. So if you take a 0 state, it will put it in a plus. 1 state, it will put it in a minus. Okay. And one more important gate would be a C naught gate. So this is nothing but an if then kind of operation. So if the first qubit, that is the control qubit, is a 1, then the second qubit, that is the target qubit, will be flipped. Does anyone have a doubt? I hear someone unmuted.
So can you present this deck instead of going through this at this smaller?
Okay, perfect. Yes, I'll do that. Yep. Is it clearer now? Perfect. Yeah, sorry about that. Okay, so the reason why I'm going through this really fast is because you already know about it. So as a refresher, there's a CCX gate. That is, there are 2 controls now and 1 target qubit. And this is called a Toffoli gate, which is similar to an AND gate in classical domain. So whenever the first 2 qubits are 1, that's when the third qubit will be flipped. So that is an AND gate. And yeah, this is the main slide where I want to introduce the idea of converting something that you already know, that is how does a classical adder work, and see how we can make a quantum adder out of it. So if you look at a classical adder that is on the top right corner, as you can see, there's A, B, S, and C. So you can see that the sum, that is S, is 1 whenever only one of the qubits is 1. And as you can see that the carry is 1 whenever both the qubits are 1. So doing, like from what we have seen before, doing an AND is nothing but doing a Toffoli gate. So instead of AND, we'll put a Toffoli gate over there. So if you look at the diagram below, that is the gate representation, you can see that the first gate is a Toffoli gate, and it's putting the answer on the carry bit, that is the C bit. And whenever you need to find the sum, you just do a C naught and you'll get that sum. So the reason why we're going through this is this ideology will be used whenever we're trying to construct something called an oracle. So in the algorithm that we're about to learn, there'll be a black box that is called the oracle, where you'll have to put your questions. Basically, you'll have to search for the answer that you're looking for. And let's dive right into it. Okay. So I think the first thing that I'm going to do is I'll stop sharing here and share on my iPad. Just give me one sec. Yep. Are the notes visible? Okay, cool. Okay, so I hope everyone has access to this. It's in the GitHub repository. It's a .pdf file which you can find. And in the start, I've given a small cheat sheet so that whenever you need to come back, you can check and see how each of these gates are at. Okay. And we've just seen how we can transform classical logic to a quantum logic. So whenever we need to do an operation that is AND, we can just do a Toffoli gate. And whenever we need to do an operation that's a XOR, we do this specific gate. So why does this do the XOR gate? If suppose this was 1, suppose this was 1, and even this was 1, then the first C0 will get activated, it will flip, and then the second C0 will also get activated and flip it again. So it will cancel, and that is what we see over here, that is a 0. And whenever only one of them is a 1, then only one of these C0 will get activated, and then we'll get the specific one that we require. So this way we can get a XOR gate, and we know that whenever we need to do an adder, we can utilize an AND gate and a XOR gate to do it. Okay. Okay, so let's try to understand what type of problem we are trying to solve by utilizing Grover's algorithm. So we have a huge search space, and now we have to find a specific state in that search space. So I'll give a complete idea on what do you mean by finding, but for now, let's just say it's a needle in a haystack, and it's what is the chance that you'll be able to find that needle? That will be on average n by 2 queries have to be done. You'll have to check on average n by 2 times, which is of the order n. Whereas Grover's algorithm can do it in the order root n with only root n queries. And this is what makes Grover's algorithm good. Though it is not giving us a speed up that is exponential, so it's not amazing, but at the same time, it is giving us a good enough speed up that can be shown in quantum computers today. Okay, so now let's look at how do we represent a search function. A search function is nothing but what you see down here. That is, the function outputs a 1 whenever we input the value that we're looking for, and it outputs a 0 whenever we get any other value. So using this, we can construct something called a search function. And one thing that you should note is a search function doesn't have to search for just one query. It can search for multiple. So here we could have x0, x1, x2, etc. But for now, let's only consider the case where you're searching for 1. Okay, and how we'll go about this is we'll look at a few terminologies, understand them, and then look at the complete algorithm. Okay. So let's look at what an oracle is. Oracle is nothing but, as you've learned, all operations are unitary operations. So oracle is a black box that takes input some state and then gives some state output, and it's a unitary operation. So based on what type of question you have, for example, if you look down, there's a question that says, create an oracle that outputs a state 1 on the third qubit. So we want the state 1 on this third qubit when the input on the first 2 qubits is 1, 0. So if I put 1, 0, then I should get a 1 over here. And for any other value, I should get a 0 over here. So let's look at how we can create such a circuit, basically. Okay, so what do we need? We need to make sure that whenever there's a, okay, so let's say I put a 1 and a 0. We know that an AND gate will give a 1 whenever both the qubits are 1. So whenever we put 2 qubits as 1, it gives a 1, and it doesn't give a 1 for any other case. And let's utilize that idea. So let's say that we want a 1 only for the state 1, 0. So now let's convert this state 1, 0 to a state 1, 1. So if you put an X gate over here, if you put that specific X gate over there, then we know that the state 1, 0 becomes 1, 1. And now you put an AND. So by doing this, now you have constructed a specific oracle, which in a way is searching for the qubit 1, 0. Qubit state 1, 0. So whenever the qubit state is 1, 0, it will give a 1 on the third qubit. and whenever the qubit state is anything else, it will give us 0. And one important point that I have missed over here is that the ancilla is 0 in this specific case. Okay. And so Grover's algorithm has a few steps in it. The first step would be something called, okay, thank you for asking that. What is an ancilla? Ancilla qubit is basically an extra qubit. So if you look at it, the input is only 1 and 0, but we are utilizing an extra qubit to save our answer. So the reason why we do this is, in quantum computing, usually we have very less qubits in our computer. So we want to reutilize them. If suppose we're doing an operation which won't let us reuse it, then so basically we have to make operations in such a way that we can negate the effect that has happened. So for example, as you can see, this qubit will always remain the same because it's just a control. So there's no operation on it. Whereas on this qubit, you're doing an X operation. So to negate that effect, you'll do another X operation over here. Whereas you wouldn't be able to do it if suppose this was your output qubit. So for that reason, we are storing it in an extra qubit and then getting that output out so that you can reuse the circuit later. And one more place where ancilla qubit is used is, we'll see it later on, if we have to do a specific circuit in which the complexity of the circuit is quite high as compared to the input. So instead of having just the inputs and outputs, we might have to utilize 4 to 5 other qubits, which in the middle of the process, so that we get the answer out. And those are called ancilla as well. Yep.
I'll add one point to it, Rana.
Yes, please go on.
So quantum computing is a form of reversible computing, which means that at any point in time, unless you have not done a measurement, you should be able to reverse all the operations that you did and get back to the initial state. So in that setting, what happens is that you cannot use the same qubit that you define the system to be in. So in this example that Rana has, the system is defined as 2 qubits. So through the life cycle of that system or the algorithm, those remain as those qubits. You cannot use it for something else. In classical, these are not reversible circuits that we have in classical. You can have convergence, fan-in, fan-outs, everything is possible. They are not reversible. Typically, you don't have this issue per se in classical. There is no idea of ancilla as such in classical. It typically shows up in the reversible computing framework, where a given qubit has to remain that qubit, and you can't use it for something else because it has to be a reversible computing machine. Ancilla, as was mentioned, essentially means an extra on the side. What that means is it's not part of the system qubits. It is not part of the things that we store as registers at the end. It is just being used to do something, and then we flip it back to the main system of qubits.
Yep. Thank you, Shesha, for that explanation. And just to elaborate on that, if you look at this specific...
Shesha, can I add something?
Yep, please do.
Ancilla is the thing that if you have irreversible functionality, to make it reversible, so you can use that in the extra bits as an output that may be garbage and may not be garbage, but it making that it's a reversible information. I think Shesha, you will agree about it. But once I getting that irreversible property of a circuit, you can use the extra input bits for making it reversible.
Yes, Kamal, that's exactly right. And that is what I was trying to say. That is, in the classical setting, the XOR gives an output of 1 for both of these values. So once we do the XOR operation, we will only have this number 1, and we won't know what the input state is. So in that case, it's irreversible. Whereas we have used an extra qubit, that is the ancilla qubit over here, to make this circuit reversible. That is, we still have the inputs with us. Okay, let's go forward, and we'll just look at, so in Grover's, there are multiple steps. The first step is putting everything in an equal superposition. So you're doing a search in, suppose, 1,000 entries. You have to make sure that all 1,000 entries are equally probable when you measure. That's the first step. And after that, you do something called a phase flip. Let's just look at what it is and come back to how it fits in into the complete model later. So to do a phase flip, we take something called a minus state. So that can be achieved by taking a 0 state, putting an X gate on it, making a 1 state, then sending it through a Hadamard, and then you get minus state. So you can do that. And if you look at this minus state and apply an X gate on it, it becomes this specific state. That is 0 becomes 1, 1 becomes 0. And what this looks like is it's just a minus of the existing, of the initial minus state. So this way we have generated that extra phase on the end, which we will utilize to pinpoint. That's what I'd like to think of it. We are pinpointing the answers that we're looking for. That is the next step. And it's done by phase flipping. So here's a question that is, we have to convert this specific state that is an equal superposition of all those states into an equal superposition, but with a minus over here. So how do we do that? We have learned how, okay. So let's just look at this specific circuit. And in this circuit, we get a 1 every time there's a 1, 0, right? So if suppose instead of having a 0 here, we have a minus state, let's say. And we know that doing an X gate, so this operation is nothing but an X gate. So doing an X gate on a minus state gives us minus of minus, which will happen only when the initial state is 1, 0. So in fact, to do this specific operation, that is convert this equal superposition into a superposition with the minus over there, all we have to do is initialize the ancilla to a minus state and then apply this specific circuit, and then we'll get that output. So you can try it out on your own in your free time. Okay, cool. So now let's just look at how the complete algorithm works now that we know a few steps in it. So first step, obviously, you have to initialize the whole, the computer to an all 0 state. And then you put it in an equal superposition of the search space. So we'll see that to do that, we usually consider the whole, all the search space would just be from 0, 0, 0 till 1, 1, 1. And then we apply something called a flip on the face. So that is what we've learned before. So we take a minus state and then put an X gate on it whenever we get our specific input that we're searching for. So when we get X equal to X0, we put an X gate on this minus state, and then we get a minus adjacent to that state specifically. Okay, and then there's another state that is, there's another step that is called the diffusion operator. So we just saw that initially we take this state, put it in an equal superposition, done. And then we know how to put a phase flip over here on that specific state that we're searching for. And now we do this step 4, that is the diffusion operator. And what it actually means is we're doing a flip about the mean. So let's understand how step 4 works. So right now we are at this specific state. Okay, so that is the state that I'm looking at over here. Everything is in an equal superposition. So this is not absolutely accurate, but it's an illustration that will help you understand. So let's say that the probability of finding each of these states is equal at this point, and obviously the mean will be the same. And now when we do the phase flip, let's say S is the state that we're looking for. When we do the phase flip, that becomes minus, right? Now we know that the mean will decrease by a slight amount, obviously. And now if you look at what happens is, let's say we are doing this operation, that is we are doing a flip about this line, but the line that you're measuring about is this line. Okay, that's something you should keep in mind. So we are flipping about this line, but measuring about this line. So let's say we flip this state about this line. That will go all the way up there. But then we are measuring about this line. So we're actually measuring that much. So have you seen that basically the probability of finding that state has increased by doing this specific operation that is nothing but a flip about this line, which is the mean. So how do we mathematically represent a flip about a mean? Okay, so let's say, okay, mathematically what actually happens is if the state is V, minus V plus 2A is the output of flipping it. And you can look at it. So this is V, it's actually, okay, that is V. and this is A. So we have V, it's actually minus V plus A. We do minus V plus A. This is minus V plus A into 2, that will be this whole thing. And then you have to reduce this, whatever this value is, and that is V. So you get 2 times of minus V plus A plus V, and finally you end up with minus V plus 2A. So the reason why I'm telling you this is, classically you can think of flip about mean by looking at this specific diagram. And you can also look at this classical example to see that it works. So you take an all equal state, do a phase flip on this 10, and then you do minus V plus 2A for each of those entries, and we get 2, 2, 2, but 22 over here. So we have increased the probability of measuring it. But the next question is, how do we implement this on a quantum computer? So for doing that, this operation is for each entry, and this operation is for all the entries at once, if V is that vector with all the V's. And obviously, like, this is a unitary operation. So now we have to figure out how do we implement this on a quantum computer, because multiplying a state with a unitary operation, nothing but doing that operation on that state. So just for your understanding, I've given how the A matrix looks like. The A matrix is just on each and every entry, there is a 1 by n, where n is a complete search space. Okay. Okay, cool. And now, now we know that we have to figure out how do we substitute this on a quantum computer, that is minus A plus 2A. And we can look at it in such a way. We can just take the Hadamards on each of those qubits outside, and then this is what remains. I would suggest you just calculate it by hand, as we are obviously running kind of short on time. So if you do that, all you have to finally figure out, we know how to implement all the Hadamards. All you have to figure out is how to implement this. And there is a mathematical theory behind it, but let's not get into it. Let's just see what that operation does, right? This is the operation. If we apply it on a 0 state, that is a complete 0 state, you get a 0 state, because this times this is 1, this times this will get that 0, minus 0 plus 2, you get this. Whereas you do it on any other state, you'll get minus of that state. This is all you have to remember. When we are applying it on a 0 state, you get that 0 state. When you're applying it on any other basis state, you get a minus of that specific state, okay? So we have to figure out how to generate an equation that does that specific flip, okay? Let me just write it down. And this is the operation that does the negative of minus I plus 2A. So you can just think about it, because if you put an all 0 state, this will become an all 1 state. And then this 1 state with H becomes minus. And you know that when you do an X on a minus, you get minus of that. So when you give a 0 state, essentially, you get a minus 0. And when you give any other state, this won't get activated. That is, this X gate won't get activated, and thus nothing will happen. Okay. And now let's just look at how the full circuit looks like. So initially, you have to put it in an equal superposition. That's what you've done over here. And then you take an ancilla qubit, that is this one, and then you put it in this minus state, so that whenever you require a phase flip, you just put an X gate on this specific thing. Okay. And then you have to construct this oracle based on your knowledge of what you're searching for. So you've seen previously that if you're searching for a 1, 0, you can construct it in such a manner. And obviously you'll have to construct more complex oracles to search for specific digits. And then you have the diffusion operator. So this is, one second, there's a doubt. Okay, when I say phase addition, I just mean that, yeah, you're right. We are putting a relative phase in the middle. So as you can see in that example, everything was in a plus plus equal state by 2. and then I wanted you to convert it by putting a minus in front of one of those states. So that relative phase is what we're looking for. So whenever you want to increase the probability of a specific state showing up, you put a minus in front of that state. So the first step would be put it in an equal superposition, create this minus state so that you can do that do that X gate on it later on. Then you create your oracle such that it does a C naught on this specific minus state only when you what you're searching for, that is when X is equal to X0, that is when it does that operation. So that way you will flip it by putting a relative phase over there. And then the diffusion operator, you don't even have to think about it. You know that it improves the probability of the state showing up if there is a minus in front of it. So that is what Grover's algorithm is. I know I have gone a bit fast, and please feel free to go through these notes again, and I've sent other stuff as well that you can look at. And
So
there's
one
one
quick comment on Bhargav's question on relative phase. It's important to understand that relative phase is very, very fundamental to why quantum computing can do some things better. And it's very, very, it's coming from quantum physics in a deep way. The reason is if you had a global phase, it will all cancel each other. It's not going to add anything new to what you didn't know. This relative phase is what helps you. I don't know if you guys have done this 2-slit experiment, double slit experiment, where the probabilities add in one place, cancel in other place, and you get this very uniquely wave-like probability distribution. Though it is truly of wave mechanics in nature, but in principle, what happens in quantum interference is this addition and cancellation of probability amplitude. For it to cancel, you need this negative sign somewhere, right? So there needs to be some cancellation. So somewhere you're cutting down on the probability to adding the probability on one state, right? Somewhere you have to reduce, somewhere you need to add. For that to happen, the interference kind of activity to happen, you need that relative phase. And that's through which, if you had some negative signs in some states, then if you add other positives, that will secularly decline, and it will add up in another place. That's how quantum interference works. So that relative phase is what is critical to make this all work in quantum setting.
Absolutely. Thank you for adding that, Shesha. Okay, let's just answer a few questions at this point. Full circuit right now. Yep, you are right. In fact, I haven't written the qubits that we are measuring. And let me just write that here. We are going to measure these qubits. So we'll only measure these qubits and we won't be measuring this. And that is why it's an ancilla. Yeah. Okay.
So think of ancilla as essentially a scratch pad. You're using it to make sure it can do things in a reversible way, but really at the end you throw it away. You really don't care about them. So it's essentially a scratch pad.
Yep. And thank you for pointing that out, Praveen. First an X, converting it into one state, and then adding a Hadamard there. Thank you. Okay, so that concludes the explanation of how Grover's works. Now let's go into the code and see how you can run it on different platforms. Okay. Okay, so I believe if you have cloned the repository, these are the items that you will find in Grover's algorithm. Grover for 4 qubit is just an extension, is just telling you how to apply, how to implement the circuit we just learned. So, okay, so there is one important thing that looks like a lot of people are thinking about, that is the ancilla qubits. And if you look at this, I've explained what are the ancilla qubits and how many qubits I'm using for input and why. The reason why we have 2 ancilla qubits is because if you remember during the circuit, during the circuit there was this specific multi C naught gate, right? So in a quantum computer, obviously, it's not possible to have all specific states being applied from the pulse level. So how a quantum operation happens is you send a microwave pulse and then that specific rotation happens. But we cannot design such pulses for any specific qubit, or we can, but it'll be too expensive. Just like how in a classical computer, if you go down in the abstraction layers, you'll only find ands and ors, right? You won't find any type of operation. So for that reason, for us to be able to do this multi-CT gate, that is multi-controlled Toffoli gate, you need extra qubits such that the operation can happen. And I'm just going to throw this word out, that is, you can figure out how this looks like by using something called an unroller or a transpiler. So these are two words you can Google, and in the documentation you'll find how to do that. And then you can see how this circuit is actually implemented using single qubit gates and CNOTs. So the hardware gate set for IBM Q computers, when I say hardware gate set, I mean the gates that are being used to build the computer. So the actual gates that are being done are only a U3 gate, which is any rotation that you can do for a single qubit gate, and a CNOT. So these are the only gates that are there, and you have to utilize them to do any specific operation that you require. Okay. So this is mainly for your, just to test it out. So you can just create a quantum register of size 7, classical register of size 4, and we're doing a H gate, that is a Hadamard on each of those qubits. So that is this first operation, that is we're putting everything in equal superposition. And before that, we're also doing an X on the ancilla qubit, which makes it into the state 1. And then because you're doing a Hadamard on all of them, Hadamard is applied and we get a minus over there. Okay. And then you are, this is actually the most important step in Grover's algorithm, that is building your oracle, because that is where you use your brain to encode your question into the quantum computer. So the question I've given over here is check, you have to check for the state 1010. So how would we do that? If you get a state 1010, let's use the same technique we used before. The second and the fourth qubit are 0 at this point. Let's make them 1 by putting an X gate. So now you know when we get a 1010, you will get an all 1. And you know that when we do that multiple controlled Toffoli gate, when all the controls are 1, then this operation happens, that is the X happens. So all you have to do now is make sure that all ones go into this multi-CT gate that is over here. Okay, so for that reason, what I have done is I've just put a 1, I put an X gate on the first qubit and I put an X gate on the third qubit, where the numbering starts from 0. So I basically put an X gate over here and an X gate over here. That will convert it to a all 1 state, and then this MCT will get activated if the initial input was 1010. I hope that is clear. If it's not, try to play around with this. Put X, put X at different spots. You don't have to put it at this specific spot over here, and then you'll see that, okay, this doesn't do what you want it to do. And also one more important point, as Shesha was mentioning, every operation, we'll try to keep it as a reversible operation. And that is the reason why I have done the same operation that I've done before on 1 and 3 below over here as well. Okay. And some of you might be wondering, what is this QC.barrier? QC.barrier is nothing but these lines that you see over here. And what is its significance is, as I've told you, this circuit is not the final circuit. It will be unrolled or transpiled into smaller gates. If you don't want it to unroll into smaller gates, then we put this specific thing called, the barrier, basically. So the optimization step will not happen between two sides of the barrier. It will only happen on each of those sides. Okay. Yep. So you can, if you have access to it, please go ahead and run it, and you'll see that it'll work. And at the same time, you can, so first what we're doing is, as Rahul mentioned, we are using the Quasum simulator over here. That is a simulator that is running on your device right now to execute the job. And the number of shots that we're using is 1000. So there's one important point that we should probably look at, that is, Rahul has mentioned there are a lot of simulators, for example, the Unity simulator, where you wouldn't require the number of shots, because what the Unity simulator is actually doing is, as we have seen, it's multiplying those matrices to get the output, and it's giving you the output. Whereas the Quasum simulator, what it does is it acts like how a quantum computer would actually act. It would randomize the process and measure those specific qubits, and every single time you'll only measure and get one output. So then if you do that thing about 1,000 times, then you can get a specific distribution that you were looking at when Rahul did the histogram, basically. And you can get the counts out of here. And if you look at the histogram, the state 1010 has the highest probability. In Qiskit, the nomenclature is twisted. So instead of 0101, it's actually supposed to be 1010. Yeah. Are there any doubts at this point? I think I've heard people trying to ask questions. Okay, so what's begin? Okay, it doesn't matter how I did it. So I guess your doubt is, oh, here I put 1 first and then 3 next.
Yeah.
And
Yes.
Yep. And then I did a 1 here and 3. So what this operation is doing is it's just putting an X at that specific qubit. So what is actually happening? I'm putting X at 1, X at 3, doing the MCT, and then I'm putting X at 1 again. Anyway, there is no correlation between this line and that line at all, and it doesn't matter. It's as we go in time, you're just putting the gates such that it negates the effect of these gates. I hope that has cleared the doubt. Okay, awesome.
Yeah, and thanks for that question. I think that's also, again, some of the subtleties of quantum computing comes through in a more complicated circuit, where the ordering will be important because that changes, especially if you have entangled state. It can change some things if you do certain operation before and after, especially prior to a 2-qubit gate. So in this case, since in the nature of things, what we want to do is, when you applied this inverter at the beginning on the gates, that is to help the oracle to catch certain specific bit of interest. And then because he was the default state, it's not explicitly mentioned here, but default every state at the beginning is assumed to be state 0. You sort of flip it back to that state as it were. In this case, it doesn't matter, but in general, ordering matters, especially if the ordering is done before or after 2-qubit gate. That can significantly change things. So that's something that you need to keep in mind, especially working in quantum computing.
Absolutely. And in fact, I would recommend that everyone, there are a few resources over here, and the first resource, that is the Quantum Challenge 2019. You can check out all the problems that are there. So we have taken most of our material from here, and the final week, there's a question which will answer all of your, all the questions that you have, basically. So we will be using so many qubits that we will have to reuse qubits. And for that reason, we will have to clean them. That is, as you said, there's an X, I'll have to clean it again so that I can utilize it later. So I would suggest you look at this problem. It's really, really interesting. Yeah. Okay, so that is how, okay, so coming back to it, we build the oracle, and then we do the diffusion operator, which is nothing but applying all the H, all the X, then a H, multiple CT. You can look at it right here. So from over here till here, that is your diffusion operator, which will improve the probability of those specific states which have a minus, and that will do the circuit for you. And one more point is, I've only done it once over here. I would suggest that you go home and repeat the circuit a few times. You will see that it'll the probability will increase till a point. Because it's a simulator, you will not have too many noise problems, but it'll increase till a point, and then it'll start decreasing again, and it'll almost be periodic. So for that reason, they say do O of root n. And if you want to know how many times you want to do it, just look at that formula -v + 2a and empirically try to find out the maximum by differentiating it, and you will understand. why it's overflowed. And there are other methods for doing it as well, using the amount of angle that you're intercepting at each of these operations. But I find that the most interesting. Yep. And after you're done running, you can just check the states. I'm not doing this specific thing. So as you see, I'm only doing it on the Quasm simulator. I'm not doing it I'm not even doing it on the IBM Q Quasm simulator. That is the simulator that is running on the cloud, or I'm not doing it on an actual quantum computer. So let's look at how we can do it on a specific quantum computer as well. And for that reason, as the name of this talk was understanding how to do real world problems, right, using quantum computing. So for that reason, let's take a problem which is called the max cut problem. This was in week 3 in that competition that I mentioned. It's the same notebook, so you can look at that as well. So the problem of max cut is they will give you a graph. Now you have to draw a line cutting the the edges of these graph such that the line doesn't cut itself basically, and you have to maximize the number of edges that you're cutting. So for example, if you take a graph that has 3 nodes and it's connected in that specific way that I've mentioned, that is 0 and 1 are connected, 1 and 2 are connected, we can see that if we draw a line through just 0 and 1, it's cutting only once. Through just 1 and 2 also, it will cut only once. But there is a method where you can cut it through 2 nodes, through connections, and that will be a max cut. So it is a contrived problem because you already know what the max cut is, but this can be circumvented later as well. So let's just keep in mind max cut is 2. Now let's try to see how we can solve this problem on a quantum computer. First thing would be encoding this problem on the computer, right? So for doing that, what you do is you're counting the number of cut edges, right? So this specific circuit over here, first it'll basically put it in an equal superposition, and then you'll get a 1 in the third qubit whenever only one of them is 1. So if you get an input as 1, 0, then you will get a 1 in the third qubit. So this is nothing but the XOR operation that we saw earlier. You can look into how the circuit works over there. So the reason why we're doing this is we are encoding our problem as the first. So if it's on the left side, then it has a 0 value. If it's on the right side, it has a 1 value. So what we'll do is we'll take 3 qubits. We will put it in an equal superposition. What that means is you're putting it in all possible states in this graph. So that graph can have 1 on the left side and 0 and 2 on the other side, or the other way. And you're putting it in all specific states that are possible. Okay. And then you have to count the number of edges that are being cut. So we know that this specific circuit will check the number of, will be 1 whenever there's an edge being cut. So if it's 1, 0, then we know that one node is on left side, other node is on right side, right? So if only one of them is 1 and the other is 0, then we know there is a cut. So that's the, okay, I think there's a question, maybe I'm not clear. Oh, sorry, that's not meant for me. Okay, so basically now all you have to do is do this specific thing for the connection between 0 and 1. Do the same thing for the connection between 1 and 2. Both of them store it in ancilla qubits, as we mentioned. So I'm storing whether or not these are on different sides of the line on this qubit. And similarly, I'll do the same thing on the other qubit. So qubit number 3 and qubit number 4 will have 1 when there are 2 cuts basically. So how do we figure out the max cut? So we know that when qubit number 3 and qubit number 4 are 1, then there is a max cut happening. That is, when both of them are 1, we need some kind of idea that, okay, this is our answer. And for doing that, you can just put an AND gate. An AND gate will give a 1 only if both the inputs are 1. So if you look at this purple gate that's on the end, the Toffoli one, that is what it's doing. So it's taking qubit number 3, qubit number 4, and when both of them are 1, qubit number 5 will have a 1. So I know it's a lot to take, but what you have to understand is whenever qubit number 5 is 1, then we know there's a max cut. So does this ring a bell? Like, does it seem like an oracle? An oracle is supposed to get a 1 whenever whatever you're searching for is happening, right? So whenever a max cut is happening, the fifth qubit is 1. So we can utilize this idea. So if suppose we put a minus state on this fifth qubit, then we're basically doing the phase flip, aren't we? And then all you have to do is the amplitude amplification step, that is the diffusion step, and then your Grover algorithm is basically done. So I would suggest you go through this again. In the interest of time, I'm going a bit fast. And let me just check. I think there are a few doubts. Okay, cool. Perfect. So this way we can create the oracle. In fact, there is one point, that is these two will not be required, because all you have to check for is, are both of them 1? We don't have to create an adder over here. We just have to check if both of them are 1. So this Toffoli gate should be enough. I think it's mentioned below as well. And as you see here, they have also mentioned the inverse of what they have done, so that they can clean the bits. It's not required in this specific example, but this is going to help you if you're going to tackle the 4th week. That is the final question. Okay, perfect. So this explains the whole algorithm basically. The initial step, that is before the first barrier, you're only initializing the ancilla to minus state, putting everything in an equal superposition. Now you are creating this oracle such that there is there's a X gate on this ancilla whenever what you require is happening. That is whenever the max cut is happening. After that is done, you do the diffusion operator, and doing this multiple times will increase your probability. Okay, so, and they're just explaining about this useful gate, that is the MCT gate, that is the multiple control Toffoli gate. Okay, that is all that they're explaining in this. One important point is, we were talking about transpiling the circuit, right? As you can see, this circuit has only U3s and C0s because it's been unrolled into U3 and CX. Okay, so you can just look at this and you'll understand how each of these gates are implemented on the quantum computer itself. Okay, and that concludes the explanation on how you can solve a real world problem using a quantum computer. The last point, I'll just take another 5 minutes. Shesha, if that's okay. That would be explaining how you have to use something from Aqua. So all this while you build the whole Grover's algorithm. Apparently you don't have to, because Aqua already has a Grover's algorithm in it. So this notebook will explain how you can utilize the existing algorithm to do your process basically. And you have to encode it in a satisfiability type of problem, and it will solve it directly. You can just look at this. I will not go into this, and I think that will be the end of my talk. Thank you for listening, and I'll let Shesha take over.
Rana, there are a few questions in the chat.
Absolutely. Yep. Okay. So transpiling, okay, difference between transpiling and compiling, the way I understand it is, compiling will take one language and convert it into another abstraction. So for example, we are compiling C code into machine code, right? Something like that. Whereas transpiling, the input and the output formats will be the same. It's just been optimized such that the computer can understand. So they're very similar, just a slight difference as far as I understand. Okay, Rana, how can we generalize this method for weighted graphs? I think there is a notebook on this. I will share that as well. And in fact, you can, right now what we learned is how to do Grovers for a type of satisfiability type of problem, right? But you can also use it for optimizing. You can go there, search for the best in that specific iteration, input it, and then do this process again. So you can solve problems like traveling salesman problem, which is an optimization type of problem as well. So that is something interesting. I'll send you the links. Are there any more doubts? Oh, okay. I understand what you're saying. I will share my screen. That is something that I have made it myself. I'm not even 100% sure about how correct it is. But the reason why I did this specific slide is to understand how they might have thought about bringing a block sphere. So a normal coin flip will give you either a 0 or 1. So it can be put on a line if you think about it. Whereas now we have one extra degree of freedom that is phase. So on each point of that line, there are infinite number of points that will have the same magnitude, but a different phase. So for that reason, I've blown it up into a cylinder. And if you look at the top point and the bottom point, these phases will be irrelevant in the sense it will be, it'll be global phase, because it is just a 0 state, and whatever phase you put here won't matter. And below it will be a 1 state, whatever phase you put here won't matter. So if you pinch all the points on the top and bottom into one single point, you get somewhat of a sphere, and that's how I think they have come up with this block sphere.
Mathematically, they are not equivalent. I'll just say this is comes out of algebraic geometry. You will see that in there. The sphere part of it should be straightforward. In a three-dimensional space like our world, you have three coordinates, x, y, and z. In the rotational basis, you have the radius and then theta and phi that explicitly points all the points in this particular thing. And if you have a fixed r that is radius, then it will be a sphere. That's the nature of it.
Yep, absolutely. So we have 2 degrees of freedom, as we can see in the example over here. And those are the degrees of freedom that are being shown.
Right. On the R is being taken out. R is implicitly assumed to be 1 because there is renormalization that happens. So that is not explicitly shown here. But if you go in the rotational basis, if you go from XYZ to R theta phi framework, they are showing just theta and phi here, but R is implicit set to be 1. At each transformation, there is renormalization happens. They always keep it to 1, and therefore R is not shown. And when you have R equal to 1, it will always be a sphere.
So that comes from the fact that we are using only unitary gates. So
the unitary gates, it preserves the probability and so forth. One quick comment on the transpiler question. I think so what is happening is in essence it is compiling in its spirit. The transpiling is more like I have a particular circuit implementation. Is the same function, can I implement it in a different way that is attuned to the hardware that I have so that I get better results. As you may know, the hardware that we currently have is still noisy. There are some operations that are more expensive in terms of noise compared to the others. And there are some optimizations also that you can potentially do to get rid of some gates if you can. And there are certain preferences on gates that you would want to do so that your probability of right answer is higher than the wrong answers. To that end, what happens is once you have reduced it to a circuit, you still do one round of transformation and see how to optimize it in a way such that the net result when you run it in actual hardware, you get a better answer in terms of probability, and therefore you do a circuit to circuit transformation that is more in tune with how the hardware responds, and therefore that is called a transpiling. The reason I said it is also compiling in one way is if you look at it, we are programming some of the things that you saw, you're programming at Python level. We didn't get to the point of showing some of the library implementations, etc. in this particular thing. We are running short, so we probably have to come back to it later. But nonetheless, if you think about it, there are more sophisticated examples that you can develop at a higher level, at Python level. Obviously, then you need to compile them into the Quasm, the assembly level language, and then have it run in hardware. There is almost an exact parallelism with how it works in our classical hardware in terms of compilation. You write in your program in any of your favorite language, be it Python, C++, Java, and so on. Eventually, irrespective of machine that you run on, Compiler translates that to some machine independent assembly level format, and then later based on the specific machine, that gets translated into the machine dependent optimization, that is the instruction set architecture that is currently available, and then you go run it. And note that optimization happens at all levels. At higher level transformation, machine independent optimization happens, and then machine dependent optimization also happens to improve the performance. Much like it, the same thing happens in here as well in terms of its flow. You could do a lot of optimization at machine independent level using some transformations. You go from one unitary to the other, that is better in many ways, cuts down on some additional gates perhaps, and so on and so forth. That is machine independent. But once you get to the circuit level, you can do machine dependent transformations or optimizations to improve your performance. It almost has a one-to-one correlation to how these work in classical as well as in quantum. So to that end, the intuition of transpiler being compiler to the one level is true, but transpiler specifically is more meant to mean circuit to circuit transformation. All right. Any other questions? So Rana, there may be some question on Oracle.
Okay, your question is, how do we create a general Oracle such that it can search any number of any number without rewriting the Oracle? Are you asking generating an Oracle which will search for which will work for any number of qubits, or for?
I suspect the question is, Oracle by definition, it gives you some answer. It doesn't tell you how it gives you the answer, which means that it somehow you encode the answer within that Oracle if you want to implement that as a function. So what you're seeing in this example that Rana did was, he says, okay, the search, the particular element that you're searching for is a specific number. Then Oracle can tell you whether you're searching for that number is there or not, right? That's what the Oracle does. It a priori, if you're constructing what the Oracle is, then you need to a priori encode that in it, which means it's a specific number. If it is a question is, can I encode more than one number within an Oracle? I suspect you can, because that's the idea of quantum in the first place. You can be in superposition of states too, but typically that's not what we use in illustrative purposes. It can get a little bit unwieldy and confusing in some cases, but you can be in a superposition of multiple states. That's a valid state too, that you can have your Oracle in. So then you can get answers to true in multiple cases.
Yep.
But
so
typically the way
I think
Oracle is used for yes and no kind of answer. If you have multiple yeses and multiple yeses in a thing, that typically is not the nature of how Oracle is generally used.
Yeah. So I just have one addition to this question, that is, as we just discussed, we knew that we were searching for the state 1010, and then we made the Oracle for it. So how is it even searching if we already know what we're looking for? So that's some question I had for a very long time. And for the answer for that, we can look at that max cut question that we've done. We did not know what the answer was before. We just knew what the constraints were, and those are the constraints that we encoded into the Oracle. And also for to answer your questions about that is, can we have a general Oracle? I'm not 100% sure what you're asking, but we can always write a Python function which will create the Oracle searching for what you require based on the number of qubits. So I think it is possible, if I understand it correctly. Are there any more questions, or have I missed any? Can you please repost them if I missed them? The coefficients of the blocks we represent. Okay, let me see what you're asking. Okay, so no, so basically that is not an easier abstraction. That is, Blocksphere is not it's not trying to make the thing easier for us. It has all specific states in it. As you can see, there's an e to the power I5. That is what will bring the complex part into it. And if you expand it as cos theta, cos phi plus I sin phi, then you will get what you're looking for basically. Yeah. Have I answered your question? Can you have a session over here? Absolutely, yeah, we can. You're right, Bhargav. Theta and phi are real.
No, theta and phi are real, yes, but what you're seeing is e power I theta, not just theta, right?
So e to the power I theta can be expanded as cos theta plus I sin theta, and that is where you'll get the complex term. So the coefficients will ultimately not be real.
And by the way, the complex numbers is critical for you to get that negative thing that he was telling you about, the phase flip, right? So that is what eventually leads to it, because I square is equal to -1. That's why you get that -1. And then once you have that -1, that's when it can potentially cancel the probability amplitudes, and therefore the probability amplitudes from some of the other states goes away and adds up in the right state that we are looking for. And you do that iteration few times, the probability amplitude of the right state converges towards 1. All right, we have 6-7 minutes. Not a lot to cover some of the other things we want to cover. So since there is an ask or request for future things, we will probably get there. But I do want to take a couple of minutes and show some of the other things that are there and cover some of the more recent advances that are happening around in terms of applications. So I thought that will be useful for this audience. So let me grab the screen for 5 minutes. I'll give an overview. And for the rest, we probably will come back in one of the future sessions and cover more at the application level. Hopefully, folks can see my screen.
Yeah.
So I'll cover some of this, give you an overview of what's going on in the industry. So there is a lot of interest in a lot of research happening across various industry sector, but I will highlight some of them here. As you can see with the dates there, they are more recent in the last 6 to 8 months time frame. Couple of industries have been more active than many others. One is the automotive industries. That's a little bit of a surprise for some of you, but I'll give you the rationale behind it. And then you have the finance industry, which are doing a lot of work in this space. Automotive industry, what is happening is there is at least in OECD or rich countries, movement from petrol or gasoline based to battery or electric based is becoming more and more real. The Teslas of the world are cornering the market, and they're getting more and more powerful. The incumbents who are combustion engine based designs, they are now want to get into, all of them have some electric offering, but getting into the market space is harder and harder. So what they are doing now is to getting in, figuring out how do I build a value proposition over and above for the exact offering the electric car offering. And they feel that battery is one space where they can bring in a unique value proposition. And so a lot of incumbents in particular are looking into the question of how do I look at a better, design a better battery if I can. So to that, they are looking at, can I use quantum computing to model a better battery? As you may all know, lithium ion is a standard by now. Most of it is lithium ion. What they are looking at is there an alternative molecular model that is available to store energy and retrieve energy efficiently? And for anything at that molecular level, invariably involves, the physics of it is invariably quantum physics. And if you want to understand that efficiently, you would want to simulate it at quantum physics level. And so what is happening is they are exploring the possibility of modeling other molecular structures in quantum to see can I simulate that and see results, and based on which I can say which may be a better option for us going forward. And so a couple of papers that are from in the recent past are from automotive sector. This is Mitsubishi and Daimler. Daimler is part of Mercedes group in general. I think they are parent organization. They are both exploring this battery technology, and this is coming from the automotive sector. Presumably, if you have a more efficient battery, you can get a bigger say in your marketplace, because it will run for much longer time. But this has a wider implication too, in terms of having better battery means green technologies gets a bigger boost. You could do many more things with green technologies if we can store energy more efficiently. One of the cost in the green technologies is that storage of energy that you capture and transportation of that storage from where the source of energy to where you consume is an expensive proposition. And that's one of the reasons why it is not as cost effective as some of the more regular energy sources are. Finance sector is interesting because they are more obviously any new technology, finance is typically the first one that moves in, because it means real dollar terms in marketplace. As many may know, even a minor nanosecond benefit could mean a big difference in finance market in terms of say fintech areas and so forth. So they go for everything and anything that is available. And in particular, a couple of things have interested the finance sector. One is in the area of option pricing. That was an application of one result that was a couple of years back from IBM. This was about Monte Carlo. As you know, Monte Carlo, the convergence of Monte Carlo goes like 1 over square root of n being the number of experiments or simulations that you do. The result showed that the convergence could, in quantum computing based solutions, could be 1 over n instead of square root of n. So you can potentially get a polynomial benefit. This could in real terms be a big difference for a finance sector. It could be, for example, some risk analysis type example. Some of the big industries run for a week on end to do their risk analysis. So anything in the prediction side of it, one popular technique is Monte Carlo. And if you want to get accuracy, which is fairly tight, then you invariably have to do millions of those experiments, and they end up running it for weeks to get good distribution. And if it means running it from weeks to a few hours or at most a day, that could be a big difference in marketplace. And therefore, that's one interest that is of great value. The other is in the space of optimization. Naturally, a lot of things related to, say, portfolio optimization, management, etc., involves optimization. Underlying technique is very similar to some of the other things that Rana briefly touched on, which was there are standard techniques like VQ, QA, OA that is used in optimization, and he was alluding to Grovers as a tuning Grovers to do optimization. Basically, the popular one VQE is used in optimization. The Barclays work here, what they did was the original optimization was unconstrained optimization, much like traveling salesperson. What they have done is extended that to do constrained binary optimization. That extension happened, and the application for that particular thing was a clearing problem. If you're not from the finance sector, basically clearing is you can have millions of transactions that happens in any marketplace. Once you do a deal, that has to be settled. The transaction settlement part of it, where actual money or some other way of buying and selling needs to be settled, that happens in the backend called clearing house. And there things get piled up, and those problems of settling is apparently very hard and very pressing for finance. So they were using that as a way to say, can I solve that problem using quantum, and can you do an efficient job? Obviously, right now, quantum is still evolving in terms of hardware, but in time, sometime, the algorithm, once you have it, as the quantum power, hardware power increases, you're going to get better and better results. It's going to scale. So their goal is, once you have a solution, you can deploy that in actual thing when the hardware is mature enough. I'm going to show one chart summarizing some of the potential use cases across industry sector. Broadly, finance is one area, and manufacturing, I would generally say manufacturing because automotive to me it falls under that category. They are the ones that are increasingly looking at it, and there is a wider other application which is in the health science sector, particularly in drug discovery and protein structure prediction part of it. These are all very useful for the society at large, especially now given the uh, pandemic situation and so forth. Drug discovery is such a hot thing. uh, had we had a quantum computer, maybe it could have helped in exploring more possibilities of the drug discovery part of it. The problem with drug discovery, much like the battery thing that I described earlier, is that everything comes down to the molecular description, which is the physics of it is in quantum physics. And if you want to do exact simulation of that using classical, as the molecule structure becomes bigger and bigger, it becomes more less and less accurate. And by and large, there is a lot of limitation to doing that in classical hardware. Even with supercomputer, you don't get good accuracy, but the scaling of the state space grows exponentially. And at some point, it will not do a good job. So in drug discovery, it's a big problem. So they get some reasonable estimate with simulation, and then they will have to actually do trial and error and figure things out. And that's one of the reasons why it's very hard to find new drugs. So the hope is that once quantum hardware becomes more powerful and available, some of these problems becomes more natural to do, especially the simulation part. The predictions part of it, disease prediction, again, underlying is that Monte Carlo thing that I was telling about. You can leverage the same piece and do some predictions better because the convergence is faster, and the number of simulations would be lesser. I will show one toy example that demonstrates that. There are many other potential applications in ML side of it. I'm not covering all of that, but underlying it is a similar technique that was used in optimization that you can tweak. There is an important result that used the same technique to do classification. Essentially, that result showed that the quality of results could be better. So now there is a nuance coming through, not just the performance part of it, but more also about even if it is noisy, even if it is not exact, can I get a better estimate compared to what I can do in classical hardware? So some of the new algorithms coming are getting more nuanced, and quality of results being one of the differentiator, not just the runtime that is generally used in many of description. One last thing I will mention before we close is one chart I want to flash to this audience. Couple of them. Quantum volume. Many a times, unfortunately, the popular press equates qubits to the power of a machine, which is not exactly true. Number of qubits is important, but there are many other factors that come into play in the hardware that is currently available. Because they are still noisy, you need to account for all the noise in the system. And therefore, just looking at qubit as equal to power is not the right way to look at it. So quantum volume is a single metric that IBM has put forward, and that by now I think is widely accepted as the measure to say what is the power of a quantum hardware. Just to illustrate that, in this example that you see here at the bottom, x-axis is the number of qubits, y-axis is an abstract error rate that we are talking about, the other metrics, the noise we are talking about. If I just double the qubit without doing anything about the noise, I don't increase the volume or the quantum volume or the power of the quantum hardware. However, if I improve my error rate by an order of magnitude, I can potentially have 500x increase in the quantum hardware power. Ideally, you would want to move across the diagonal. You do want higher number of qubits, but really you do want better machines that are less erroneous. That is also equally important. So quantum volume should be the measure of how powerful the machine is. Number of qubits is just not sufficient to describe the power of the machine. Just to mention one other thing, why a lot of interest at this time? You see on the right is the paper from Gordon Moore from 65 that plotted the initial results of how the transistor number of transistors was scaling, and based on which made the prediction of doubling of transistors every year and up to 2 years, and that eventually became called as the Moore's law. In quantum, in the last 4 years, what we are seeing is doubling of the quantum volume every year. And Jay Gambetta is the currently VP of IBM Quantum. he made the prediction that the power of a quantum hardware is going to double every year for some foreseeable time. Moore's law, as you all know, held true for good 45 years. This is likely that quantum volume, currently at least, there is no significant bottleneck that people are seeing, but we are likely to be on this roadmap for some time to come. And the other interesting part is, by the time the quantum volume gets to about 1000-ish, that's when it becomes sufficiently large in terms of its capability and power for it to match some of real world problems, and we can then start comparing against the classical hardware. By classical hardware, we mean any supercomputer that you may have. And if you sort of project it down, so we are looking at anywhere between 2023 to 2025, where we will have this hardware sufficiently powerful to do some real world problem that no classical hardware can solve. All right, so those are the few points that I wanted to mention. In maybe a minute, I'll quickly show some toy example on a couple of applications which we can get to later. So here is one, there is an important paper in 2019, March of 2019. This was in the Nature. This is classification, binary classification. What was shown was that if you had, I will give you a pointer to this. Basically what this was shown was you have the test data and you run with the initial classifier, that you can see some description. These are all that can be done efficiently in quantum, in classical. So you get some results, but keep an eye on this accuracy part. It will not be very accurate. The paper proposed two important techniques. One was to do machine learning type model, eventually, that you get trained a model and you then use that model to predict the classification, right? Binary classification. And finally, the last one was the actual SVM, support vector machine kernel. They mapped that to the quantum part, and they showed that the accuracy was much better. So if you see here, this was one of the results from the paper. This was the training way of doing it, where you train a model and then you apply it. This one has, in this case, much better result compared to the other one. You will see it will hover around 80 plus-ish. And the other one, the final one that I will show, which was to actually take the support vector machine kernel, and the kernel part of it was implemented in quantum. That has much higher accuracy. Obviously, these are all toy examples that we are currently running, but the kind of quantum power that was used in terms of entanglement and other things which are not available classically, this one perhaps is the most powerful one. You will see that this is likely to produce much better result. We will see in time as the hardware evolves how this pans out, but the likelihood is that this may do a much better job in terms of quality of results. Again, I want to highlight there is a nuance coming through now, not just the performance. Now the quality of results is also another metric that new algorithms are coming about in recent times. So you see that this new technique is providing much better performance in terms of the quality of results. One other toy example is in the finance. Remember I mentioned the Monte Carlo thing, the convergence in thing. They used it in option pricing. So this is the European call option. There is a put option, call option. What they showed was that you set some option and you run the test, right? What happens is you do simulation. You have the quantum version, there is a Monte Carlo version, and this is a small enough problem where you can solve it exactly. So you can sort of compare it correctly. But the important, so the payoff is fairly good. So one part is quantum gets to the payoff part reasonably quickly, converges. But more importantly, look at the estimation error. The convergence is very rapid in quantum compared to Monte Carlo, which is in light gray. So it would converge much sooner, and the number of samples needed would be less. If you want to have the convergence on the classical, you may have to extend it much further. So the number of samples would increase quite a bit. So that way, this convergence is much efficient, and it will take much shorter time to solve this particular problem. All right, with that, I'm going to stop. Any questions?
Hello guys, I need a photo, so is it possible that everyone switch on their camera first? I take a.
All right. Guys, if you're able to turn on your cam, please do. Yeah. Hi, Terrell. Finally, nice to meet you. Haha. All right.
Real nice to meet you.
That was really good, Rahul and Rana, and of course, Dr. Sayantan, are you here? Can you hear me? All right. Thank you, Dr. Shesha. This was really interesting. And Rana and Rahul for taking us through the technical aspect. If you guys can share the notebooks that you used today, that'll be great. I just put up a Google Drive link in our WhatsApp group. If you guys are not there, I'll put it up over here. All right. Any other thoughts, questions that you guys have? Like, we have like 3 more minutes, then we have a talk because Dr. Shesha has to. All right. What's the chances of doing a master's in quantum chemistry using superconducting qubits or even topological or photonic? That's Sean's question. Dr. Shesha, you want to take it up?
Yeah, absolutely. Quantum chemistry is one important area, potential area of application for quantum computing, naturally because quantum chemistry, as you know, involves not simple molecules, right? Complex molecules. Think of proteins, think of genomes. All these are fairly complex molecules. And once you have that, for example, I'll just throw out some rough numbers, right? If you had a caffeine molecule, which is about 24 atoms, that has something in the order of, if you want to have an exact description of that molecular evolution, you need something in the order of 10 power 48 bits to describe. And in quantum, if you had 160 odd clean qubits, it could simulate it efficiently. It's another matter, we don't have clean qubits, but nonetheless, 10 power 48 bits, which is classical, means it's estimated that total number of atoms in planet Earth is roughly 10 power 49 or 10 power 50. So you're looking at nearly 10% of atoms in planet Earth to simulate just a simple caffeine molecule, which basically is telling you that it's practically not going to work out. So problems in quantum chemistry involve things that are even more sophisticated compared to what I just described in caffeine, right? Much complicated. Now, if you want to go do simulation of that, it's not going to work out in classical hardware. So potentially, quantum is one place where you can get that efficiently as it improves. But then, current as it stands today, we may have to do a lot of tweaking and mapping. It's essentially a mapping problem. You go from one quantum description to the other description and have it run. That's the challenging part of it. But nonetheless, that's one area where we are more likely to see some benefit. And in fact, if you look at the origin story of quantum computing, at least quantum computing as we know in modern terms, in the 81 thing that Feynman talked about, it was about simulating quantum physics. That was the primary motivation. So it is essentially the original true sin, as it were. So you want to get to that problem, and quantum chemistry is more likely an area where we are more likely to see some application emerge sooner rather than later.
All right, so a couple more questions. Do you have time to take this?
Sure, I can take a couple more.
All right. One is by Dipanshu. So which qubit realization technique among spintronic superconducting circuits and topological qubits seems more promising for near-term applications?
So IBM is betting on superconducting qubits. There are a few others who are betting on others, but currently from the looks of it, superconducting and ion traps seem to be the most promising one. And also I have to say, it is a fast moving area, but right now these are the ones that are ahead right now. But right now there is no clear winner at this time. And it's possible that things may change as we evolve. I want to mention, for some of you who may know classical hardware, it was never a constant. The transistor was never one way of doing it. If you look at history of transistor too, in early designs, it was all bipolar transistors. Then you had CMOS, then field effect transistors came in the 90s, that took shape. So at each point there was a transition. It was always an evolution. It changed to another. At some point there was a drastic switch from, say, bipolar to CMOS to FinFET and so field effect transistors, etc. All this have happened. There was a jump at some points because it had a clear value proposition. In the case of classical, it was the integration. When you wanted to integrate more and more transistors, if you had bipolar, the power was just ridiculous. It would just burn the circuit. It was just not impossible to integrate more transistors. That's a big game changer. So the decisions were made based on those kind of things. So here also, we are on an evolutionary path. Sometimes there may be a clear winner based on some business constraints and decisions, at which time there may be a switch that can happen. So we don't know at this time. Superconducting and ion traps are the ones that are currently ahead of the curve.
Okay, cool. But Australia is also working on betting big on silicon-based circuits.
Right. Even I think Europe is also betting that. I think they have a big project going on that as well. As I said, those are slightly different in the sense that there are various approaches being explored, as I mentioned, because it is not a settled problem at this time. Various industries are focusing, but some of these like government or EU level projects are a little bit long term. Private companies will have a little bit slightly different perspective on how it goes.
Right.
So you need to understand some of those differentiation as well.
True. All right. So this is from Sayantan. Hello, Dr. Shesha. The classifier examples we just saw had only 2 input qubits and a ZZ interaction between them was used. But for multiple qubit input, the ansatz it's created keeping the hardware in mind. Is there a way to create a hardware agnostic ansatz? Nice question.
I don't have an exact answer for you right now. That could be something that we can explore and see. Look, all this area is moving such a rapid pace right now. It's hard to say exactly that. To my knowledge, no, but that doesn't mean I know everything. So which could also mean somebody has figured it out as well. But what is happening is currently superconducting qubit is one of the more popular and dominant ones. So a lot of techniques are coming with sometimes explicitly or sometimes implicitly with superconducting qubit in mind, and techniques are developed that way. But having said that, we need to explore that line of thought. I don't have an answer.
Okay. Just one more question.
Yes.
All right, cool. So what's the chance of a quantum integral differential equation similar to the quantum Fourier transformer? This is by Sean.
I don't know much about quantum integral differential equation, so I don't know how to answer that. I'm sorry.
All right. All right. Since we skipped that question, what may be the roadmap towards quantum cryptography?
So here, I'll mention few things. So sometimes, again, the Shor's algorithm and the result of factoring, there is little bit of misconception in terms of when that can happen. In some cases, I find it's when sometimes I talk to some folks with quantum computing, they immediately think Shor's algorithm and immediately think it's solved. It is theoretically solved, yes. But if I have to implement that in actual hardware, the hardware needs to evolve a lot more before I can actually implement that in actual hardware. It would require fault tolerant level quality of a qubit in terms of errors that can be there. And it also has to be able to support, obviously, error correction for it to be fault tolerant, which means the number of qubits needed with the fidelity that is needed We are not near that at this time, and not likely to be there for quite a few years now. So it's in terms of in real terms, we probably are years away from having any Shor's algorithm implemented on, say, for 4096 bits encoding. Right? That's just not going to happen right now. Uh, well, uh, anything in the future, you have to give a caveat that assuming something drastic doesn't happen, but given our current understanding, it's not going to happen anytime soon. Having said that, a few caveats, a few things that why it is important is it depends on your data life cycle, right? What is your life cycle of your data? If I were to say your and my social media account, the life cycle is less than a minute till somebody sees it, and after that, nobody even goes and looks at it, right? But there are some data that can have much longer life cycle. Think of finance institution, think of government organization, think of army and other things. There may be data sets that could have value even after many years. Think of a lot of things, that data information that is not even declassified here, right? There are, because there is some value to something in nature. So data set that have, say, life cycle of 15 years, 20 years, and so forth. Imagine that if I were a hacker today and I just grab that and store it and have that somewhere locked up, and I just sit on it and wait for quantum computer to evolve. And once it evolves, I can potentially break that and see the content, and that may still be valuable whenever I can break that. So those kind of data are the first wave where these things become more serious, and therefore naturally financial institutions and government organizations that have those kind of data sets are more sensitive to this particular aspect, because now technology is evolving. Even if it means it's going to take 10 years, 15 years for Shor's algorithm to be implemented, if your data is going to be useful as life cycle is, then they would worry about that. To that end, there is already what is called as quantum safe cryptography that is already available. This is using classical hardware itself. It's just that you're, instead of using RSA as your encoding, you're using some other algorithmic technique. There are a bunch of them available. That will be hard to, even quantum computer cannot break them, because at least in the present knowledge, there is no known algorithm that can solve that problem efficiently, much like the way classical cannot solve the factoring problem, at least efficiently in all these years that we have seen. There is no known algorithm on the quantum side. So there are techniques that are already coming, and these are offerings that are already there to do encoding in a different way. So some of them, particularly finance institutions and governments, are doing some of those as part of their encoding and putting it in database, moving that in. In the regular internet, it will take years till it becomes closer and closer to reality. There will be a shift, because currently, as I said, all the network traffic that we have, by and large, the data lifecycle will not exceed more than a month, by and large. If you see the percentage of data set that flows around in the internet. So which means by the time anybody can decode, it will not have any relevance. So that's why there is no urgency on the internet side. But at some point in the future, when it gets more and more real, obviously the standards organization will kick in, and they will want to change the encoding at that time.
Okay, perfect. Thanks a lot. And Lokesh, just to give you more info. So we are starting a separate hack series that's purely around quantum cryptography and what we can do with that. So yeah, we'll start that soon. So stay connected. Yeah. All right. Thanks a lot, Dr. Shesha. Like, any final words, thoughts?
One point, actually, if you don't mind. It's more like an announcement that is, so Qiskit is going to bring about a new competition, which is in quantum machine learning, probably around next month. So stay tuned and join the Qiskit Slack so you can get the information. Yep.
Lovely. Awesome.
Yeah, join one more thing, sorry. So join Qiskit Twitter and Qiskit YouTube for more announcement related to our new things coming up, hackathons, or perhaps local meetup, and even seminars. Thank you.
All right. Thanks, Rahul. Yeah. Okay, guys, if you can turn on your cam, we can take a quick picture. Otherwise, we'll do with whatever we have. All right, cool. That's fine. Okay, thanks, Jamie. All right, cool. Dipanshu.
Rahul.
All right, I think that's enough. Okay. Dipanshu.
Okay.
Just send me the photo. Sorry, my camera is not switching off. It says stop it.
Okay, so now instead of cheese, one, two, yeah. All right, cool. Thanks, guys.
Yeah,
Thanks
thanks for this opportunity.
Rahul and Dr. Shesha. This was really interesting.
Yep.
Sure.
Thank you.
I'll connect back with you, Shesha, again for our future connections or future knowledge series.
Yeah. Thank you, guys. Thanks for the opportunity.
Yeah. Thank you.
Thank you.
Thank you, everyone.
Thank you, everyone.
Thanks, Jamie. We can't hear you clap, but yeah, got the message.